Welcome to Mini Lecture 3 for Unit 3. In this mini lecture, we will be talking about thermal radiation. So far in this unit, we've already talked about electromagnetic radiation, what it is, its light, some of the basic properties of light, and several of the different types of electromagnetic radiation, ranging from radio waves up through gamma rays. We mentioned in both of those previous mini lectures that light is very useful for carrying information from distant objects to us. In this mini lecture, we will begin to discuss some of the information that light carries, and in particular, we will discuss thermal radiation. If you were to go out on a clear winter's night and look up, you would see the constellation Orion. Orion is made of several bright stars, and the two brightest stars are Betelgeuse and Rigel. The picture on the right is an actual picture of the constellation Orion, where the photographer defocused the camera slightly in between each exposure. And this allows the colors of the stars to come out more. And what you notice is that the bright star Betelgeuse in the upper left is definitely a yellowish orange color, while the bright star Rigel in the lower right is a bluish white color. Why are these stars different colors? It turns out that colors can tell us about a star's temperature. This is thermal radiation. Before we begin to talk about thermal radiation, we need to define a few terms. The first term we will define is blackbody. A blackbody is an object that emits electromagnetic radiation due to heat. Heat is a property of matter. It's the energy content of an object due to its temperature. Heat is not a type of light. What some people will call a heat lamp is really a lamp that puts out a lot of infrared radiation, and our skin is very good at detecting infrared radiation. So any object that has energy due to it having a temperature can be considered a blackbody. The second term we will discuss is intensity. Intensity is the amount of energy that leaves a black body from a small area every second. If I have a light bulb and it's a frosted light bulb and I turn the light bulb way up so it's very bright, the intensity, the amount of light coming from a little square of the light bulb, is very high, so that even if I were to cover all of the light bulb except that little square, it would still dazzle my eyes to look at it. We would say that light bulb has a high intensity. If we were to turn down the dimmer switch so that not very much light was coming out of that little square and it was easy to look at, we would then say that that light bulb had a low intensity. The final term is luminosity. Luminosity is the total energy leaving a light source every second, and we measure luminosity in watts. So again, back to a light bulb. A 40-watt light bulb puts out less energy than a 100-watt light bulb. So we would say that the 100-watt light bulb is more luminous. It's possible to make a 40-watt light bulb that has the same intensity as a 100-watt light bulb, but the 100-watt light bulb will always have a higher luminosity. It's putting out more total energy. Another thing we need to discuss before we go on to talk about thermal radiation is how astronomers plot spectra. So here's a nice picture of light going through a prism. You see the light entering from the left. It's sort of a yellowish white light, and the light comes down to the lower right as a rainbow. And what we see in that spectrum, which is what a rainbow is some blue light, some fairly intense green and yellow light, and then not very much orange and red light. So how can we graph this? Well, it's not too difficult. If we want to graph it, let's move the picture out of the way. First thing we need are some axes. And if you have axes to make a graph, you need to label the axes. So on the x-axis, we will put colors: violet, indigo, blue, green, yellow, orange, red. Well, those are descriptive terms. That's not really a quantity, and on a graph we want to plot a quantity. So what quantities do we know that are related to these colors? We have wavelength, and we know that violet light has shorter wavelength than red light. We can plot frequency because we know that violet light has a higher frequency than red light, but we also know that because of this, the axis would be running backwards, that higher frequencies would be to the left, lower frequencies to the right. That's okay. Another related term we could plot would be energy, because we know that violet light is more energetic than red light. And just like the frequency, here we would have high energies on the left, low energies on the right. Any one of these four things would be a valid quantity to plot in a spectrum. On the y-axis, we need some measure of how much light is coming out at each color. The typical word that astronomers will use for this is intensity. The more intense the light is, the more light that's coming out at a given color. However, you could also use the term energy, because you could say more energy is coming out at a given color, but you need to be careful not to get confused between the energy on the x-axis and energy on the y-axis. So if we have something that's very red, it would have a lot of energy coming out in the red and very little energy coming out in violet. So it's easy to get confused there. So I will tend to use intensity on the y-axis because that seems a little more intuitive. So how would we plot this spectrum in the picture on this graph? Well, we see a lot of blue light, a lot of green light, a fair amount of yellow light, and a lot less orange and red. So we would just draw a curve that shows that we have a little bit of violet light, a lot more indigo and blue light, quite a bit of green and yellow light, and then it rapidly dies away, so there's very little orange or red. This is how you would draw a spectrum, and this is how you would read a spectrum. That there is very little light here at the short wavelengths, there is very little light at the long wavelengths, and there is a lot of light at the blue and green wavelengths. So here's a picture of some various steel objects. If you had to guess, which of these would you say is the hottest and which would you say is the coolest? If you had to pick up one, which would you pick up? Well, you'd probably pick up one of the black ones. The orange ones we know from experience are glowing because they're hot, and we also know that from experience that the brighter yellow one is probably hotter than the two orange and red ones. So intuitively we already know a couple of things about thermal radiation. So let's start with this idea of the color. That in this picture the yellow object is clearly the hottest, the red is cooler, and the black ones are cooler yet. This was noticed by a German scientist named Wien. His name is spelled W-I-E-N, but we pronounce it Wien. And what he noticed is that the wavelength of light at which the spectrum of a black body has its peak, has its highest intensity, that wavelength gets shorter as the object gets hotter, as its temperature increases. Here's a mathematical equation that shows that. If we make the temperature bigger, because it's in the denominator of the fraction, the peak wavelength, which remember is that Greek letter lambda, will get smaller as the temperature gets higher. So hotter temperatures mean that the spectrum will peak at shorter wavelengths, and cooler temperatures means that the spectrum will peak at longer wavelengths. Shorter wavelengths are bluer light, longer wavelengths are redder light, so the bluer something is, the shorter the wavelength at which it's glowing, the hotter it is. And that's what we saw on the previous page. Yellow is a shorter wavelength than red, and so the yellow glowing object is hotter than the red object. So here are some different objects, and let's discuss how their temperature affects where they're glowing. Let's begin with the sun. The sun is here. The sun has a temperature of 5,800 Kelvin. Let's round it off to 6,000 Kelvin. And the sun glows yellow due to its temperature. And because it's yellow, that means that its spectrum is peaking in the yellow, which we can see in the plot of the spectrum to the left of the sun. Most of its light is coming out in the yellow, although it is putting out light at both long wavelengths and short wavelengths. If we go to the next object above the Sun, this is a star that is forming. And as such, it hasn't heated up yet. It's not hot enough to begin fusion, but it is fairly warm. It has a temperature of 600 Kelvin. That's somewhere around 600 degrees Fahrenheit, roughly. And from Wien's law, we know that because it's cooler than the Sun, its spectrum must peak at a longer wavelength. And that's exactly what the spectrum shows. We see that the peak is longer wavelength than even the red part of the visible spectrum. This object's spectrum is peaking in the infrared. And so if we wanted to study this object, it does put out a little optical light, a little bit of red light, but if we wanted to study it, we'd be better off going to the infrared and using an infrared telescope. The object above it is a cold gas cloud that is just beginning to form into a star. In fact, it's so cold we don't see any optical light coming out. There's probably a very, very tiny bit of optical light, but not even in a large telescope can we see it. This cold gas has a temperature of 60 Kelvin. 60 Kelvin is extremely cold. It's 60 degrees above absolute zero. And if we use Wien's law, we would find that its spectrum peaks at a wavelength of 48 micrometers, which is in the very far infrared, almost into the radio light. So we would use a far infrared telescope or a radio telescope to study this cloud because it's just not putting out much light to speak of in the near infrared or in the optical light. If we go down to the bottom picture, this is a very lousy picture of a bright blue star. This is taken with an ultraviolet telescope, which is why it looks kind of funny. But this is a distant star that's just very bright. It's very hot. Its temperature is 60,000 Kelvin, so 10 times hotter than the Sun. And you can see that its spectrum peaks way over in the ultraviolet, very short wavelengths. So it is putting out optical light, and we would be able to see this star with an optical telescope, but is putting out even more light in the ultraviolet. So these are all examples of astronomical objects whose color and their peak wavelength are varying because they have different temperatures.